Let's see if you are, how many came up or like were able to, did you manage to give an answer? Mm-hmm. Okay. So let's see what you answered. And whoa, I thought that I thought the signal would be more clear, but what I would say that the answer is, I would definitely say maximum likelihood estimation is the most fundamental. Yeah, it was a cool answer. It's the most fundamental, let's say, statistical theory. Let's think about this simple example of a statistical model where we want to examine a population and we want to know about the mean of this population. So what we do is that we take a sample, we randomly select a sample, we have n observations, so n values, and then we come up with this model where we say that the ith observation is a parameter, which in this case we can think of as the mean plus an error, which is then normal distributed. So that's the most simple statistical model we can come up with. And now the question is, this model will give us a probability density function. Which one of these three is the likelihood function? Oh, I need to move the, yeah. And you know the notation that for observation y, I, we take the density function and then we do something with it. And the density function is of the model, from the model. Yes, let's see what you answer. And most of you got it right. The likelihood function is defined by that we multiply these probabilities and then we call them likelihoods once we have observed them. So before the observation, the model says there's a probability of observing this. Once we have the data and we use the model and thus the density function to calculate the probabilities, then we don't call them probabilities, we call them likelihoods. So this is an illustration of the case where the red ones are the observations. It's a small example I made, so we have an observation here, here, and here. And then the model, in this case, will give us a probability density function looking like this. It's a normal distribution, and here is the mean is -2, and the standard deviation is 2.4, gives us this prediction by the model. Over here, the mean is 1, standard deviation, and gives us this prediction. Here we have some other values, and here we have some other values. And in which one of these cases is the likelihood the highest? 2 seconds. Which one of these set of values of parameters give us the highest likelihood function in this case? Or in which case? Now we see, and you're right again, most of you, it's definitely D, because that's what we do for each observation. We go in, look up the density value, probability density value of this one, and then we multiply all these together. So this one gives a higher likelihood than this one. It gets a bit nasty with the numerics when we multiply all these small values, so therefore we always take the logarithm to the likelihood, then we add the values, and numerically it's better for the computer. But you see, it's the highest likelihood value. Then, in order to do, I don't know what happened, but oh, I'm running the wrong way, sorry. We could also have used least squares in these cases. Then we would take we'd say here's the mean is -2, and then we would take the distance to the observations and square these and sum them. So that would be the sum of squared error. And in this case, we would always also get this value, because we get the, of the parameter, this parameter estimate, because we get the lowest sum of squared error. So that's a very nice technique. And then the question is, there's a difference between this maximum likelihood estimation and least squares. And which one of these three answers to that question is correct, or most correct? Yeah, I need to launch it. Time is running, so let's just quickly see what you answer. And that is again very much the most correct thing is that the answer, but it's now we're getting, it's not very trivial always to understand these differences. So we need to think about which technique for parameter estimation. There are pros and cons. We need to specify the models a little bit differently, but maximum likelihood is more fundamental. We can use any error distribution. The computations become different, and the interpretation is a little bit different. So that's some of the stuff that we really have to work in details with, I realize. So that's great. And then I have one more question, a few more questions. What about this one? You can read yourself. Two minutes. Okay. Let's see what you answered. My answer is a little bit that's really hard to say, right? It depends. On every time we have some new data, then we go, oh shit, that's an outlier. What do we do? All that stuff. Next question. What happens here? No. I don't know why. It's the first time I use this program. So then, no. Close, Paul, but there's one more question, but okay. Let's just see. The last question is this one. Maybe find something strong to drink. It works sometimes, right? Maybe the right question is call upon DTU. I think we have lots of things to do, and I'll go home, evaluate the results, and see what should be the next step in the process here with you guys. I'm making fun. Linear, non-linear models, varying over time. Interesting challenges we have. And of course, when we have the dynamics, always we must go deep into this model validation. And again, it's not trivial. So, yeah, how is the distribution? But can we quantize that with a single number, the root mean square, or this and that? Yeah, very good questions for us to work with. So, yeah, I think we've done a lot, and now I've seen we've been away from each other, and now we're coming back, and oh shit, you guys have done a lot. So first, we maybe need to get updated somehow together. Yeah, thank you. So that was a.